Hello, everyone. It is my great honor to introduce this talk, Deep Neural Network and Accelerator Co-Design, Present and Future. My name is Callie, and I'm Assistant Professor at Georgia Tech ECE. Hello, everyone. It is my great honor to introduce this topic, Deep Neural Network and Accelerator Co-Design, Present and Future. My name is Callie, and I'm an assistant professor at Georgia Tech ECE. So before we go on, what is deep neural network and accelerator co-design? Let's use an analogy first. Building a deep neural network is like baking a cake, and then building accelerator is like building a plate. And this co-design means we have a cake, and we want to place it on a plate. So we have a DNN model, and we want to deploy the model to the device. So this is the basic idea of co-design. Now let's take a deeper look what exactly they are. So for deep neural network, there's a very popular approach called NAS. NAS goes by an automatic neural architecture search. It is also known as AutoML. And NAS is really promising because it can boost the quality and accuracy of machine learning algorithms. Here are one example of an early work of NAS, that these cells are automatically searched by machine learning. So this is deep neural network design, and we will be focusing on this NAS approach. And then as we talk about accelerator design, we have different choices. We have different target devices. If we're targeting GPU, TPU, and NPU, these architectures are fixed. In this case, we'll be search for optimized or tuned neural network implementation. And if we're given an FPGA, it's more interesting because we can customize its architecture. So in this case, we will be search for customized DNN accelerators. And this figure is another early work, an example of a DNN accelerator on FPGA. So all these architectures, these structures can be customized. So this is accelerator design. And co-design is to build a bridge between these two and hope that these two can be happening at the same time. It's a little bit more abstract, and let's use the same analogy to see if we can understand it better. So talking about co-design, there are 3 levels of co-design. Let's go back to this cake factory. The level 0 co-design is that there's no co-design at all. It's like you're baking a cake, and after that, you're building a plate. And now you're putting the cake on the plate. Well, things can go wrong. Maybe your cake is too big for the plate. And what's happening that you have to go back to the factory and bake the cake again. So this is an iterative approach. It's very wasty and time consuming. Now we want to be smarter. We come to level 1 co-design. Then now when we're building a cake, we have something in mind. We keep the size of the plate in mind, that based on this estimation, we decide how large the cake we want to build, right? So we've built the cake with the plate size in mind, and then we build the plate and we place them together. Well, this is smarter, but things can still go wrong. What if the plate is different from expected? Sometimes we have the wrong estimation. In this case, we still need to go back, but this is already better than level 0. And now we have level 2. Things get much smarter. Then now we try to bake and build in pairs. We're doing the same thing at the same time, the 2 things at the same time. Now we bake the cake, and at the same time, we build the plate. And if we want something different, we build the cake and build the plate at the same time. So in this case, the cake and the plate can be in pairs perfectly. So this is much better. And if we go back to the DNN accelerator design using this analogy, let's see how it looks. So at level 0, there's no design at all. So the first step is using the pure NAS to design a deep neural network. We conduct a neural architecture search, and then after that, we move to accelerator design. So this is 0 co-design. And if we want to be smarter, let's recall the plate. We want to have, when we are baking the cake, we want to have an estimation of how big the plate is. So at level 1, things are similar here. We do a NAS, and we want it to be hardware aware. So we call it hardware awareness. So during this hardware awareness, when we are doing the NAS, we have something in mind, hardware cost. And this is based on an accelerator evaluation that we have a model and we want to estimate how good or how bad it performs on the real hardware. So based on this guidance, we may come up with some search DNN, and then eventually we still need to build the accelerator because we didn't design that. We just have an estimation evaluation. So this is level one. And of course, things can still go wrong that the estimation can be not accurate. And then we have this level 2, smarter way, that we want to achieve a true DNN and accelerator co-design. And how is it different? Now here we see this DNN search and this evaluation of this architecture search are merged into the same design space. They're combined together. So what's the difference is here we have a DNN, we have an accelerator, we search them, we combine them together. And then during the search, the DNN is changing and we also change the accelerator. And now we're still not happy. We keep searching, that we change the DNN and we change the accelerator. So everything happens all at the same time. And the output of this co-design is a searched DNN plus its accelerator. And then eventually, when we're moving to the real implementation, we only need to do a fine tune of the accelerator. So this is level 2, a smarter way of doing the co-search. And of course, we don't like level 0. So let's take a look at level 1 and level 2 again. What's the difference? The difference is, I'm pretty sure you're aware of that for at level 1, the hardware awareness, we have a fixed accelerator. The accelerator itself is not searched, is not changing. But the difference in level 2 is that, fine, okay, now the accelerator design can also change. So during this co-search, both DNN and the accelerator are changing, are being searched. So that's a major difference between level 1 and level 2. And of course, level 2 is more challenging. And because it's more challenging and is more interesting, and it leads to more optimized design, our main focus of this talk is level 2. That how can we achieve a true DNN and accelerator co-design? So what do we need for achieving this goal? Apparently, we're going to need 2 parts, right? The first part is we're going to have to know how to do the neural architecture search from the software. And then we have to know how to do the implementation search at the hardware side. And then we have to combine them together. So for software, we have NAS. And then at hardware, we have implementation search. And if we combine them together, we get nice. And this nice is really the key focus of this talk. Now, next, we're going to see why this nice is nice and how are we exactly going to do to achieve this nice goal. So this is a big picture of how nice is supposed to work. Nice is a true simultaneous NAS and implementation search. So assume we have a nice engine. What we'll be expecting is we get these solutions in pair. So solution pair 1, we have 1 DNN and its corresponding implementation. For solution pair 2, we have DNN 2 and we have its implementation 2. So these solutions are generated in pair and also automatically. So this is how nice works and why it is good, because first, it enables this one-click AI because everything is automated. So we have automated AI algorithm deployment, development and deployment. Everything is automated. And the second is we have good AI now. Because the software and hardware are generated together, we can bridge the gap between software and hardware for higher quality solution. So this is what nice looks like, and this is why nice is nice. Now let's come to the key design methodology for this co-design. Why it is challenging and how can we solve that? Well, why it is challenging, I think it's very obvious that for software, we have a neural architecture search space, and for hardware, we have an implementation search space. Both spaces are really huge. They're hard to explore. And when we're combining them together, we not only double the search space, but we improve the complexity by a lot. So that's very challenging. And how we're going to do that? Well, we have a couple of smart ways to do this co-design, to apply this code search at the same time. So method one is, how can we do something that we want to find something in the middle and connect to both software and hardware? Say this is a software design space, this is the hardware design space. We want to find this, something in the middle that connect to both. And then this will be the key to solve the co-design. So this is the first method. And then this is the second method. The second method is even smarter, that can we merge the two space together like this? Now they're completely merged into one search space. And can we formulate both problems in one equation in this merged space? So if we can do that, we can just search them naturally in an automated and simultaneous way. So for both methods, we have some representative works, and I'm going to briefly introduce both. So let's take a look at the first method. This is the representative work for an FPGA and DNN Co-Design. It's an efficient methodology for intelligence on the edge. It seems to be the most cited in this conference, but I'm not sure. I didn't verify that, so don't take my word. So this is the first work, FPGA and DNN Co-Design. It's a prototype of a co-design framework. So what exactly are we gonna do, and how do we do this FPGA DNN Co-Design? Let's see. The key is to find the something in the middle, right? And how do we find that? So we have two parts. We have to design a DNN, and we have to design an accelerator on FPGA. So for DNNs, based on our experience, that we know that DNNs are usually built by repeated or similar basic blocks. For example, we're all familiar with ResNet. ResNet is stacked, or let's say constructed by repeated this residual blocks. We have one residual block and we just repeat it for a couple of times, so we have more layers. So our experience is DNNs are usually built by repeated or similar basic blocks. This basic block is the key. And then when we come to the accelerator on FPGA, it's very similar actually. The accelerators are also usually built by processing elements. We call them PE. For example, this is an illustration of an FPGA accelerator that we have different PEs here. We have PEs for convolution 3x3, we have PEs for convolution 1x1, and so on and so forth. So we have this group of PEs, we have the accelerator, because these PEs can be reused by different layers. So this is how accelerator is constructed. This is how DNN constructed. Where's this something in common? It's here. DNNs are built by basic blocks. Accelerators are also built by PEs. So the connection here is PEs will be used to implement the basic blocks. So this PE, this basic block, they're basically the same thing. We'll talk about that later. They are the key here, that something in the middle that we're looking for. As long as we can find this basic block plus PE here in the middle, we can solve these two problems at the same time. Now let's take a deeper look. What does this basic building block sitting in the middle, what does it mean? So what we want is, we hope that this basic building block can be used to determine DNN and used to determine the FPGA accelerator. And how do we do that? Well, this is an example. Suppose the basic building block look like this. It's just a bunch of sequential layers, come 3x3, come 1x1 activation, and so on and so forth. So assume that we already have this basic building block. Recall how we build the DNN? We replicate it. Right? So we have this basic building block, we replicate it for once, twice, and 3 times, and so on. So by replicating it, we can have this DNN architecture. So this is how we use the basic building block to build a DNN. And next is how we use this basic building block to build accelerator. Well, the answer is also simple, because we already know the architecture of the basic building block. We can come up with this accelerator that has instances for each layer, right? We have conv 3x3, we have a PE for that. We have conv 1x1, we have a PE for that. So this is the FPGA architecture. This is the FPGA implementation. And this implementation is exactly used to implement this basic building block in the DNN. Right? So this is how this basic building block, as long as this one is decided, the DNN is decided, and the accelerator is also decided. And then the DNN and its implementation is connected together. So the next question, very natural, that how do we choose these basic building blocks from a large design space, right? So now this is the key technology. How do we do that? Because we have multiple different choices of this basic building block. How do we choose that? Well, we have a framework, DNN FPGA Co-Design framework that we have two engines. The auto DNN engine is a co-search, and this one is used to generate the DNN model. And then we have an auto HLS. HLS is just the way to write or to design the FPGA accelerator. Is not super important. So we have another engine here to generate the FPGA accelerator, right? So the first engine is used to generate the DNN model. The second engine is used to generate the hardware accelerator. And this engine is responsible for choosing the basic building block. As we said, this is quite important. So there are 3 steps. I'm going to briefly go through them. Before that, the auto HLS is to generate the accelerator automatically. And apparently, we're going to need some accelerator template. And I'm not going into detail. So, but this is the illustration of what does the accelerator look like. And now this is the key. The key part is how do we find the best building block, and how do we use this building block to build the DNN? Let's use another analogy. That suppose you have a job interview, you have to go a couple of steps, right? You do not just talk to the manager. So we have CV screening, and then you probably get a phone interview, and then probably you are gonna be invited to the company to get an on-site interview, and finally you talk to the big boss. So similar here, we are choosing the best building block, and we are gonna divide them into different steps to filter out those unpromising blocks as early as possible. It's just like a job interview, right? So the first step is we wanna do a basic building block modeling. We wanna provide performance estimation of a DNN using these equations. And then the second is we do a very quick search. We roughly use this building block to build DNN and roughly train them. The goal is to only keep promising ones to reduce the design space. And this is an example of the training example that for each basic building block, we have these dots, and we only pick these ones at the Pareto curve. So this is the second step. And the third step is now we have narrowed down the promising blocks. Now we are going to do a much more fine-grained DNN search and update. So in this case, or in this step, we are going to perturb, train, and slap DNNs with performance constraint. For example, you want to achieve 30 frames per second or 15 frames per second. You want to target a big device, and you want to target a smaller device. Okay, so this is how we're going to do in 3 steps. And now let's see how it works. Let's just jump to the experiment results. How it works, we're gonna demonstrate a nice victory using this real world contest. It's a design automation conference system design contest. We call them DEC SDC. The goal of the task is object detection on FPGA and GPU. It is held by already a couple of years. So how did we do? Our first attempt in 2018, we won 3rd place for FPGA category, 3 out of 51. It's not bad, but it's not so good. So what did we do wrong? Is we independently designed DNN and FPGA accelerator. Well, it's a lot of iteration and it's really a pain in the neck. So we only got 3rd place, and lesson learned. Okay, so this is the key motivation of the co-design. We really went through this painful process. And now we become smarter. After we learned how to do the co-design in 2019, we actually won the double championship for both FPGA category and GPU category. We won both. And this is really a nice victory. And we thank NICE that leads us to this victory. So it turns out that, well, this co-design actually works and it's very helpful. And we do have some medium coverage and open source code, and feel free to check them out. All right, so this is the first design methodology, co-design, that we want to find something in the middle, and this something in the middle can be connected to both software and hardware. And we use this FPGA and DNN Co-Design to demonstrate how we do the co-design. And then the next method we've been talking is a smarter one, right? So we want to merge the two design space like this. They're completely merged together. And we want to formulate the both design space in one equation. And why we're going to do that and how we're going to do that? Let's see. The big picture is now we have software architecture search space, we denoted by A, and then we have hardware search space, we denoted by I. And ideally, we want to put A and I into one formulation, preferably they're differentiable. And then by doing that, we want to solve A and I using continuous optimization together. It's very elegant. For example, we can use gradient descent to solve this merged design space. And this is a true nice work. And I'm going to briefly introduce that. So this is the formulation. We talk about that we want to merge the two design space into one. And how are we going to do that? We come up with a merged formulation. So this is the existing formulation for hardware awareness. And this is our nice formulation. And this formulation is for true co-design. So what's the difference here? Well, this part, let's see. This is the loss function. This is the minimization target. And the first part is architecture search space, architecture loss, accuracy loss. And this part is, well, sort of the same. But what is not the same here is, this is the performance loss. This performance is used to evaluate the hardware performance, right? How the model is performing on the real device. So in the existing formulation, we see the implementation I0 is fixed, and it is not in the search space. Recall what we said, this is the first level of co-design, that we have the hardware in mind, but it's not searched, it's fixed. It's like when we are baking the cake, we have the plate in mind, but we are not actually building the plate, right? So this is the first formulation for the first type. And then this is the formulation for the second type, that here in the performance loss, this I, this implementation variables I, it's, well, it is also a variable, it's searched, it can be searched. So this I has an impact on the performance, and of course it also has an impact on the accuracy, for example, the quantization, the bit width. And finally, we have a resource constraint. If I have a larger device or if I have a smaller device, the constraint will be different. Okay, so this is the difference between the true co-design formulation and the hardware-aware NAS formulation. Now the challenge is, how do we formulate implementation as differentiable with respect to the loss function? Okay, and we all know how to do A. I'm gonna introduce in 1 minute. We know how to do A. And how can we do this I? Well, the answer is not quite hard. Let's see. So this is the differentiable DNN architecture search, differentiable NAS. This is a quite popular approach already proposed by existing works. So how does it work? Very briefly, we have a DNN, we have a couple of blocks, and then for each block, we have candidates. We have a couple of candidates, and for each candidate looks like different. So our goal is to choose one candidate from this pool, right? But now you see, this is a discrete solution space. How do we choose? How can we solve this discrete solution space using continuous optimization? Well, the solution here is to convert or to relax from discrete to continuous. For differentiable purpose, what we can use is Gumbo softmax. So using this Gumbo softmax, we have some sampling parameters here, theta, for each candidate, and these operations will be sampled following the Gumbo softmax distribution. And of course, these sampling parameters are differentiable with respect to the loss function. Okay, so this is how the existing work proposed to use a differentiable search for NAS. Well, now let's come to the implementation. The implementation, one example of implementation search is a quantization. So for example, you want 18-bit or you want 8-bit or you want 4-bit for your accelerator. Can we search that? Well, yes, we can. So we have Q1-bit, Q2-bit, and we can select from one of them, right? So the same question here. This is discrete solution space. And how can we convert this discrete to continuous? Same answer here. We use the similar technique, Gumbo softmax. And then the next question. Well, I want to throw in more implementation search variables. How can we do that? The answer is we can put other implementation variables in this block. Well, for example, let's say it's IM, and as long as we can formulate this block's performance, and we can formulate its resource, and as long as this formulation here, F and G, is differentiable with respect to the loss function, we can also change this other implementation variables during the search. So we are skipping the details here, but we can, for example, we can search the parallelism factor, and it's very effective. Okay, so this is the big picture, that we use differentiable NAS and we use similar technique for differentiable implementation search. So now, since everything is differentiable now, it's very happy that NAS is differentiable, that implementation search is differentiable. What we can do is we can use some very elegant continuous optimization now. We call them, for example, we can use gradient descent to minimize this loss function. So this is how we achieve this true co-design, by formulating everything as differentiable. And this is how it works very briefly, that we have a couple of different DNNs searched targeting different devices. We have GPU-oriented DNNs, we have FPGA-oriented DNNs. And apparently here, for GPU-oriented DNNs, they achieve the shortest GPU latency, and for FPGA-oriented DNNs, they achieve the lowest FPGA latency. And it turns out that this co-design is very effective. And this is just a visualization of different architectures targeting different devices, and they look quite different. And this is just a couple of follow-up works using differentiable approach. And after that, it's becoming very popular to do a differentiable co-search. And this is just a very quick Google Scholar search. And there are a lot of interesting follow-up works using this differentiable network and accelerator co-search. And we believe that differentiable approach is very, very promising in the future. Okay, so this is what we have right now so far. What is, we talked about how to do a nice work. We have software and we have hardware implementation search. We combine them together and we have this very nice approach. And we demonstrated that this nice approach is really effective. And now the question is, what is next? What is in the future? Well, my personal answer is as follows. The first point is now we are seeing much more complicated DNN models. In the previous design, we're only seeing one model. It's like one cake. Right now, we're seeing a much more complicated scenario. We have multiple cakes. Why is that? Because we have this multi-modal, multitask models. I'm going to give an example soon. So the model is becoming much more complicated. And next is the platform is also being complicated. Now we have more than one plate. it's like now, now we have more than one plate. So it means now we have heterogeneous platforms, and we must apply this mapping aware nice. I'm going to give an example of this as well. So this is in the future, that NICE must be able to consider multi-modal, multitask models, which is more complicated, and the device, the platform, is also becoming more complicated. So a very quick example, what does this multi-modal, multitask mean? So multi-modal means the model is trying to process and relate information from multiple modalities. For example, this is a robot. It will process information in sound, in image, and also with motion. So this is multi-modal. And multitask means the model is trying to learn multiple related tasks jointly so they can apply knowledge transfer, or they can share weights, they can learn together. And these are two examples, two classic scenarios for multitask model. And apparently it's much more complicated than a single model, with more branches and with much more parameters and layers. So this is the complexity for models. Of course, because we have multi-model, we have multitask, we have largely increased complexity in the future model structure. And then this is the future of platform. We're already seeing a lot of heterogeneous platforms by now. For example, on the left is a Xilinx platform. What they have is they have some scalar engines, they have configurable adaptable engines, and they have different intelligent engines, AI, DSP engines. So this is apparently heterogeneous. And same thing here for Tesla. This is a cheap example from Tesla. And they also have heterogeneous chip. So they have one GPU here, they have a couple of neural network accelerators here, and they have 12 CPUs here. So apparently this is also heterogeneous now. So given these future devices and platforms, we're also seeing a largely increased complexity in heterogeneous platforms. So now, when the MMT, multi-modal, multitask model meets heterogeneity, well, things get much more complicated. We have largely increased complexity in model structure, and we also have this largely increased complexity in heterogeneous platforms. Okay. So now, because the increased complexity, now mapping starts to matter. The scheduling starts to matter. And then, of course, the optimization of each device also matters. Well, it matters since a long time ago. So the NICE, the future NICE, must be able to incorporate mapping formulation and scheduling formulation, and maybe there's something else. So this is the future open questions for NICE. So this is just a very quick example. I'm not going into detail, a very quick example of NICE plus mapping formulation. The much more details are talked about in this invited paper. So this is how we can formulate NICE together with device mapping in a differentiable way. And I hope, of course, this is still an open question. I hope this can be solved in the near future. And another example of NICE combining mapping and scheduling. So this is also our latest work that we already proposed something called heterogeneous model mapping, heterogeneous model to heterogeneous system mapping with communication and computation awareness. So this is just the backend part, the mapping part. And can we incorporate this mapping and scheduling into NICE framework? And this is also an open question. I do hope we have follow-up works targeting this problem. So a brief summary, what do we have in the future is NICE plus mapping, NICE plus scheduling, NICE plus implementation optimization. And here are some reference papers that that already discussed this integration, or potentially can be integrated. So this is what I have in mind for the future is NICE plus MMMT plus heterogeneity. So this is the brief summary of the talk. We cover some basics. We covered DNN and Accelerator co-design. We introduced 3 levels of co-design. Of course, we have we like level 2, the smartest one. And then we talked about this NICE approach simultaneous neural architecture and implementation code search, we demonstrated this nice is really nice. And then we talk about what's going to happen in the future. In my personal opinion, it is when multi-modal, multitask models meet heterogeneous platforms. It's going to be much more interesting to incorporate this MMT and heterogeneity into this nice framework. So that concludes my talk. And if you have any questions, please feel free to reach out to me at Georgia Tech, this Sharc Lab. Thank you very much, and thank you for listening.